was we'd have two hands-on sessions, one about multiple GPUs and then one about debugging. But the one about debugging fell apart. I will take the credit or blame for that because I couldn't get DDT working on site, so I couldn't set anything up. That's not entirely my fault, but it's at least partly my fault because I didn't.
You could try to debug this.
Yeah, my debugging strategy was call the guy and say, how come our debug server isn't working? And he says, well, I'll get right on that, for some definition of right on. But that wasn't soon enough. So I've got a short presentation about debugging, and most of it is, the second part is actually a presentation that one of our engineers did a year ago at GTC, and it's his slides about debugging. And then if you want to use DDT, he's got some information there about how to use it. But I will be perfectly honest, I have never used successfully, I have never used DDT. I used something else, but I have used CUDA GDB, which DDT interfaces with, but I've never used DDT itself. So I'm not speaking from a position of strength. This is uncomfortable for me. But before we get there, these are the common errors that we see with OpenACC programs. You say it's parallel and it's not. You're referring to something out of bounds, so you've moved data to the device, but it wasn't the right data bounds. Stale data, that's a common one. You're missing an update. Some of you probably saw that yesterday. Present error, so if you refer to some data, this is really the same thing, data bounds errors, only it's or you say the data is present and it really isn't. So I know some of you saw that yesterday. And then the program will die. That's unfriendly. Roundoff error differences, either I mentioned this yesterday because there's some roundoff error differences between host and device. Now they're both IEEE, so roundoff error should be exactly the same, except not all the transcendental functions are implemented exactly the same way. So the arithmetic is the same, but transcendentals are not necessarily bit exact. And I mentioned yesterday the fused molad issue. So if you're comparing host to device, because you want to make sure your execution is correct, you need to take those into account. And then for things like accumulations and summations, they'll be accumulated in a different order, so you'll get a different round-off answer, so the answer will be different. So you'll need to determine whether that's significant. Okay, async errors, typically it's because you're doing things asynchronously and some other things not asynchronously. I think I mentioned last week we had a customer saying this program doesn't work. So, well, if you put async in all your directives, then they'd be on the same queue and they'd execute in the right order. Okay. Compiler error, that still happens a lot. A large fraction of the compiler errors you're going to run into are because you're doing something that we haven't implemented and we don't have messages in the compiler that we haven't implemented this. So things like computed go-tos, for instance, that will be available in 15.9. But before 15.9, you would just get a very unfriendly message from the compiler. I have no excuses. There's reasons. There's no excuses, though. Right? These things should not ever get into a product. The reason is we're pushing fast on features and performance as fast as we can, and the things that we haven't done, we haven't pushed as fast on to at least even tell you that we haven't done them. And then other real bugs you can run into. This is where you want a debugger. And so one of the questions that someone come up is, how can the compiler or runtime or whatever system help me with all of these things? And we have a plan, but they're not all implemented. So things like the async error, we have a flag to tell the compiler, ignore all the async clauses. Then it'll run them all synchronously. And that's how I found this bug. You ignore all the async clauses, it works. Put in the async clauses, it doesn't work. It's probably an async error. Things like parallelism errors. Well, we're going to, at some point, put in a flag to say, run everything on the device, but run it sequentially. And if it works sequentially and doesn't work in parallel, then it's probably a parallelism error. The roundoff error, our intention is we haven't done this, is to work as hard as we can to make the device bit exact with the host. There will be a significant performance penalty. Things like summations will have to be accumulated sequentially. Some reductions don't, like max and min. It really doesn't matter what order you accumulate max and min, but some in product, it does. Nobody does product reductions. Anybody do product reductions? It's a stupid idea, right? You'll go completely off the end. You'll have overflow before you know it, or underflow, I suppose. It also means things like the transcendentals we'll have to re-implement to make them bit exact with what the host does. Some other things, data bounds errors. I think I mentioned yesterday, we have an idea of how to do this, but it requires hacking Valgrind. So, and stale data, same thing. We have an idea of how to solve the stale data problem, but again, it involves hacking Valgrind, and that's an issue there. Okay. So let's talk a little bit about debugging. And this is at least partly a CUDA Fortran talk, and I'm going to skip over some of this because these are not my slides. We know about the three ways in the CUDA Fortran and OpenACC members and OpenACC, and this is a nice little something or other. All right, so, and here's the code that we generate. We generate x86, and we used to generate CUDA C and run that through. And how does one debug that? Well, you don't, because CUDA C doesn't know where the program came from. And so this is particularly why we went to this LLVM intermediate form. So now we're generating LLVM IR directly, and we can put dwarf information in here. So that's what the debugger uses. And so that was the significant motivator. There really isn't any performance advantage or penalty for using one or the other. It's really for debug information. And we generate information about line numbers and global variables. So theoretically, when it all works, you should be able to look at your program. If it crashes, it'll give you a line number backtrace. You can print the values of variables and arrays. If you're debugging CUDA Fortran, it's a little bit more well integrated into CUDA Fortran than it is with OpenACC, because the CUDA Fortran source is the CUDA source you're generating. The OpenACC is it's one generation removed, right? You're trying to debug host code inside OpenACC. So we've had the debugging available in CUDA Fortran for a while now, and that's pretty mature. There are some limitations. You may want to dial down the optimization level because the back end optimizes variables away. When it optimizes the variable away, you try to print the value of I, and oh, there is no I. It doesn't even give you information that there used to be an I and it's not available, just there's no variable I. And so that's the back end that we don't control, so we don't really have any way to control that. And here's OpenACC. Oops. And it roughly generates a kernel that looks something like what's on the right-hand side there. So it has arguments corresponding to the arrays referred in the loop, and then it computes indices from the thread IDX and block IDX and generates code that looks like that. Now, if any of you followed that instruction over there and looked at the actual generated CUDA C code, it doesn't look anything like this, but roughly it's a similar structure. So we worked really hard to try to keep source line correlation between the generated CUDA code and the original source line code, variables in the generated CUDA code and the original source line code. And what do we do with compiler generated variables? There's a lot here going on. But there's been some stuff available. It's been available for a little over a year. It's not perfect. It's got some limitations that we have addressed a few of these, but not all of these. And we've done integration with Allinea DDT. So we love DDT, abstractly speaking. I can't say I use it very often, like never. And even if I had been trying to use it, I would have noticed that we didn't have a working license server for it. But okay, there's the marketing slide for DDT, and it's great. So, and this is where, if I were doing a live demo, I would have shown you the live demo, but I'm not. Blah, 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 blah. Compile with -G, O0, and same thing with OpenACC. Compile with -ACC, O0-G. And here's where he shows some of the uses of Allinea DDT. You can set a breakpoint. Now this is CUDA Fortran. And you can set a breakpoint on your CUDA Fortran line and dive down in there, evaluate some data, print the values of scalar variables. It's got some pretty classy ways to view arrays, for instance. You can view it as a matrix or a table. You can view it as a graph and display it that way. And then here's an OpenACC version. Set a breakpoint. Now, I don't think you'll be able to set a breakpoint on, say, the parallel loop lines, because those loops have gone away. There's no code generated for that. That's not strictly speaking true, but it's not what you'd think it might be. When you look at the value of the array A there, well, A is now turned into a pointer to device memory. So that's actually a device pointer on the right-hand side over there. And you can inspect the, here I'm inspecting the array B here as a table, and I don't know what I'm doing here. This is something with, these two slides are the same. All right, this is more CUDA Fortran, CUDA Fortran, CUDA Fortran, visualization.